All right, so this video is going to go over pages 10 through 12 in your sound or waves part 2 packet. So what is an echo? What causes an echo? So think about where it usually happens. So an echo is basically a reflection of sound from a hard and smooth surface, from hard and smooth surfaces. Okay, so if you've ever been in a big empty room when there's nothing in there, okay, you actually hear more echoes because in a full room where there's people, objects, and stuff, a lot of those things absorb sound waves, so that's why you don't really hear echoes. It's like in a cave, there's nothing really in there besides air and hard walls. Okay, so reflection is just basically sound waves, or an echo is basically sound waves reflecting off of those hard surfaces. So the speed of sound at 20 degrees Celsius is 340 meters per second, while the speed of light is 3.00 times 10 to the 8 meters per second. So how will this relate on why sound has echoes and typically light does not? So if sound is a wave and light is a wave, wouldn't light naturally behave like an echo? So the truth is it does. Okay, so there is some sort of delay. There's a bounce back. There's a reflection. But you got to think about how fast it's going. So speed of light is much faster. Okay, so there is a delay. Okay, but it's so minimal that there's basically no delay, or one that you could detect with your eye. So basically no delay. Sound moves fast, but not that fast. So that's why you can say something, okay, and you wait a couple seconds and it comes back. With light, it'd be very far less than a second. So it'd be like really fractional of a second. Number 3, a C note has a frequency of 264 hertz. So there's F. Find the wavelength. So you're looking for wavelength. If the temperature is 25 degrees Celsius. So I have a temp. So right now I'm looking for frequency. I'm looking for wavelength. I have frequency. I'm looking for wavelength. So I'm probably going to do this one. V equals frequency times wavelength. But if you notice, I don't have V. But I do have a temperature, so we can figure out how fast is sound moving that temp. So V equals 331.5 plus 0.6 times 25. Okay, and you get a speed of sound of 346.5 meters per second. Now there's my velocity. Now I can plug in. So 346.5 equals a frequency of 264 times my wavelength, which I don't know. So divide both sides by 264 and you get a wavelength of 1.3 meters. Number 4, the speed of sound in air increases with temperature. This goes up about 0.6 meters per second every degree Celsius. Explain why. So we talked about in this last video is if you increase temp, what happens is your kinetic energy or the movement energy of molecules goes up. Okay, so think about it's a relay race. I'd rather have fast people than slow people. Okay, so if it's warmer, those molecules are moving a lot faster. So if you're doing a relay race, they're going to be able to hand off the energy a lot quicker. So naturally, your velocity is going to go up as well. Number 5, in many science fiction movies, when a spaceship explodes, a loud sound is heard by the occupants of a nearby spaceship. Is this realistic? Why or why not? It would be a no, because sound needs a material medium. It needs air, it needs water, it needs a solid, it needs some type of molecule, and space doesn't have it. Space is a vacuum. So it needs a material medium. Number 6, when a sound wave with a frequency, so I have a frequency of 440 hertz, is sent through steel. A wavelength is 11.66 meters, so there's wavelength. What's the velocity? So I'm going to do V equals frequency times wavelength, so pretty basic math here. So V equals 440 times 11.66. Okay, and we get a whopping 5,130.4 meters per second. Now, if you notice, we're still talking about sound here, and what we've been dealing with is right around that 340 range, average-ish. But now we're talking about a sound wave that can move over a 5,000 meters per second. Okay, so remember we talked about air is very poor at transferring sound because the molecules are very spread apart. In a dense, hard material like steel, molecules are densely packed. So think about a relay race again. It's real easy if your relay partner is standing right next to you. You don't even have to run to them. You just hand it off. Okay, so if I were to rank the ability of sound to move through a state of matter, Okay, solid would be my number 1, followed by a liquid. And the slowest speed of sound would be a gas, okay, which is your air. Okay, so moving on to the next one. An automatic focus camera is able to focus on objects by use of ultrasonic sound wave. The camera sends out sound waves that reflect off distant objects and return to a camera. Okay, a sensor detects the time it takes for the waves to return and then determines the distance the object is from the camera. If a sound wave with a speed of 340 meters per second, so we have our velocity, returns to the camera in 0.15 seconds after leaving the camera, how far is it? So you have t, and you're looking for distance. Okay, so I have v, d, and t. So naturally we're going to do v equals d over t. But this is one you got to be really careful with. Anytime you're talking about things bouncing back or echoes and stuff, what happens is it took me 0.15 seconds to go from, so let's say it started here. Okay, here's your wall or whatever the object hits. It goes here, it bounces off and comes back. So that's your total time to hit both there and back. But all I'm doing is I'm asking for how far is it from where you started to where it bounced off. So what you're going to do is you're going to divide that time by 2. Okay, so your time is actually going to be 0.075 seconds because that's how far it took to get there, and then it took 0.05 seconds to come back. So be really careful with the echo problems. Okay, if I give you a total time and it's talking about something bouncing off an object and coming back, you need to split that in half. Okay, so now I can do 340 equals my distance, I don't know, and my time is 0.075, not 0.15. So my distance is going to be 25.5 meters, and there you go. Okay, so I promise you, please be careful of that. I promise you I'll see it where they just put in the time and they think that's it. You got to cut it in half. On number 2, on a hot summer day, a pesky little mosquito produced his warning a sound near your ear. The sound is produced by the beating of its wings at a rate of 600 beats per second. What is the frequency of hertz of the sound wave? So cycles per second is frequency. So your answer would just be 600 hertz. This was just to kind of get you to notice that frequency basically means number of waves per second. Okay, so now assuming the sound wave moves with a velocity of 350 meters per second, what's the wavelength? So V equals frequency times wavelength. So V is 350. Okay, my frequency is 600, and wavelength, I don't know. Divide both sides by 600, and you get a wavelength of 0.58 meters. 3, true or false, doubling the frequency of a wave source doubles the speed of the wave. False. Okay, if I were to double the frequency, that means wavelength could go down. Okay, it would go down by a half. Okay, but the only thing that affects speed of a wave is by changing the medium. Okay, you'd have to go from like a liquid to a gas to a solid. Frequency and wavelength have nothing to do with speed at all. Okay, so just be careful of that. The only way you can change speed or velocity is by changing the medium. Number 4, playing a C note on the middle keyboard produces a sound with a frequency of 256 hertz. Okay, there's your frequency. Now I know my speed of sound is 345. What is the wavelength? Okay, so all I'm just going to do is plug in. So 345 equals my frequency of 256 times wavelength. Divide both sides by 256 and you get 1.35 meters. 5, most people can detect frequencies as high as 20,000 hertz, assuming the speed of sound is 340 meters per second. There's V. Determine the wavelength of the sound corresponding in this upper range. Okay, so I have a frequency, I have a velocity, so I'm just looking for wavelength. So my velocity is 340, frequency is 20,000, and wavelength, that's what we're looking for. So wavelength that we could hear, okay, wavelength would be about in this case, I was looking the wrong answer. That would be 0.017 meters. Okay, number 6, an elephant produces a sound, 10 hertz sound wave, assuming the speed of sound is 345 meters per second. So I have frequency, I have velocity. What's the wavelength? So a lot of practice here. 345 equals 10 times wavelength. Okay, divide both sides by 10, you get 34.5 meters. Okay, determine the speed of a sound on a cold winter day. Temperature is 3 degrees Celsius, so V equals 331.5 plus 0.6 times 3, and you get a velocity of 333.3 meters per second. Okay, number 8, Miles Tugo is camping near Glacier National Park. In the midst of the Glacier Canyon, he makes a loud holler. His echo is 1.2. He hears his echo 1.22 seconds later. The air temp is 22 degrees. How far is it? So you're looking for distance. So this is that whole V equals D over T again. Okay, so there's going to be a couple steps here. Is one, remember we talked about echo. If you want to know how far the object is for an echo, you got to cut this time in half. Okay, so your time is going to be half that. So it'd be 1.22 divided by 2, and that'd be 0.61 seconds. Now, I'll also give you temperature, so we need velocity. So velocity equals 331.5 plus 0.6 times my temperature, which is 22. Okay, so I get a velocity of 344.7 meters per second. Okay, now I have all my pieces, so I'm going to do 344.7 equals distance, I don't know. My time is 0.61, multiply both sides by 0.61. And my distance is 210.27 meters. 2 sound waves are traveling through a container of unknown gas. Okay, wave A has a wavelength of 1.2 meters, and wave B has a wavelength of 3.6 meters. The velocity of wave B must be blank compared to velocity of wave A. Okay, so their wavelengths are different, which means their frequencies are different. But remember, velocity can only be changed by the medium. It didn't mention they're both in the same container of gas, so there is no change in medium, so they have the same velocity as each other. So remember, you can have different frequencies and different wavelengths, but still have the same velocity. Okay, so only if you change medium. Number 10, 2 sound waves are traveling, so same thing. So wave A is 1.2 meters long, wave B is 3.6 meters long. So that means wave B, its wavelength goes up by 3. So it's 3 times whatever wave A is. So that means the frequency of wave B had to go down by 3. So divide by 3 or a third. Okay, so your answer here would have been B, 1/3. And that'll end that one.